Hello, welcome back to Quantum Computation Simplified. I'm Kadiresan. In this video, we'll learn about molecular simulation and VQE algorithms. What is VQE? We'll see it later. Why quantum molecular simulation? It's because of this need that is doing molecular simulation. The quantum computer is existing today. It all started from Richard Feynman's, the famous physicist statement that nature is in classical, damn it. If you want to make a simulation of nature, you'd better make it quantum mechanical. And that is the starting point for people to think about quantum computer. Okay. And later, of course, when Peter Shor and Grover came out with their algorithms, uh, we saw a lot of advantages of quantum computer, but the original intention was to do molecular simulation. Okay, let's try to understand as much as possible what exactly it means. Okay, we know that molecular science is governed by the dynamics of electrons, atomic nuclei or protons, and by their interactions with surrounding electromagnetic fields. And this study is applicable to different areas of science: molecular physics, chemistry, biochemistry, and material science. Of course, one question can come to our mind is, yeah, these areas have been existing for a long time and there are a lot of developments taking place. Why should we look for molecular simulation? It's because quantum systems cannot be accurately simulated with classical computers. Let's take an example, okay? A simple molecule of sulfuric acid, H2SO4, has 15 protons and 15 electrons in it. To simulate the behavior of electrons along with the influence of protons, we need to have something of this quantity, 2 to the power of 100 quantum objects we can say, and each object, if you want to represent in a computer, may take two real numbers. It's not 100 quantum objects, 2 to the power of 100. Why? Because each electron will be affected by the remaining 49 electrons, and each electron will be affected by 50 protons. You know, there's a complex relationship, right? So for that you need this many number of quantum objects. If you want to store those values, how many bytes of memory required? I really do not know what is it called. I think 2 to the power of 40 bytes is 1 terabyte. So you can imagine, just to model a simple molecule of sulfuric acid, you need many bytes which you can't even imagine. And when you want to develop a new material, say for green battery, or when you want to develop a new drug, you can imagine it will be a very complex molecule involving many atoms. So it's just not possible to do a theoretical simulation. So currently what people are doing, qualitative understanding of the functioning of biomolecular machinery is supported by extensive experimental results. So scientists are doing a lot of experiments because they just can't do the complete simulation. They get some input, but finally they need to do a lot of experiments. Okay. But if you can do some detailed quantitative physical simulations using a quantum computer in parallel to detailed experiments, we'll have a better understanding of molecular functions and we'll be able to develop new materials or new drug very fast. Okay. Continuing further on this topic, we can say chemical processes and procedures in biological sciences can be perfectly simulated in quantum simulator or quantum computer. And we don't have to depend on serendipity. It's a new word I learned when I was going through some of the literatures. So what does it mean is, many inventions or discoveries happen by just by accident. One example, we can say that penicillin was accidentally invented by Alexander Fleming. So today we have to depend on a lot of luck or accidents to get our problem solved, which can be avoided, okay, using quantum computer. Each qubit can be mapped onto a specific electron or proton to study the molecules. Quantum entanglement can be used to describe electron-electron interactions without approximations. So you may ask me, okay, today we don't have too many qubits, and if you want to have a qubit for an electron, it's not possible. Yes, people are also working on how to reduce the number of qubits required. In this NISQ era, the calculation time for the energy of atoms and molecules scales exponentially with the system size. We have seen the system itself grows exponentially, right? When you want to do the simulation on a classical computer. But if you use quantum algorithm, it will expand polynomially. So these are all the advantages what you see here. And as a software engineer, you really do not need to know more about the the electronics or the molecular physics. You can still program it. That is what we are going to see it in the video. But it's better if you know these things. You can do research on your own, or you can support other scientists easily. So what's the current status? So initially people thought we have to do analog quantum simulators. It's something similar to analog computers we had maybe 40 years back to solve differential equations. We couldn't proceed at that time because of noise issue plus scalability issue. Similarly, in analog quantum simulator also had a lot of issues. First of all, it has to be built for a specific purpose, meaning to represent a specific system, and it's affected by decoherence, meaning losing its stability, and error correction and fault tolerance mechanisms are not there. That's why scientists switched over to digital quantum simulator. Like 40 years back, people switched over to digital computer, right? And this is easy. We are all familiar. So we'll start with some qubits in ground state and put some gates to simulate. So that is what is being done. Okay. So now, what's the approach for molecular modeling? How do we do that? What are the steps involved? Before going to the steps, we'll try to understand some physics part of it or a chemistry part of it. Okay. Again, I'm not an expert, so I'm not going to the detail, but let me take a simple example. I'm sure you'll be able to understand. So this is a graph giving relationship between the energy of a molecule with respect to atomic distance between the atoms. So in this example, we are considering two atoms. When they are very, very close, it will possess a high energy, and as it gets separated, at one point of time it will have the least energy, and that's the stable condition or stable state, and atoms will be in equilibrium. And with higher energy it will be unstable, and if you increase the distance between the atoms, like, then there may be a slight increase in the energy, but it also will be unstable. Okay, the energy is in general measured in the units called Hertz, and the distance is measured in angstrom. So what is Hertz? It's 27.2 electron volt approximately. So what does it mean? The electron volt, it represents the kinetic energy of an electron when you apply a 1 volt potential difference. Okay. Similarly, 1 angstrom so given in a known unit, micron, we are all familiar. So it is 0.0001 micron. Okay. Now you would have got some idea about what we are going to do. So basically we'll be defining an atom, like how many electrons are there, how many neutrons are there and things like that, and what is the distance between the molecules. And we can also define some more parameters we'll see later, and then see where it gets settled, so that you will come to know the ground state energy. So in order to do that, we are going to use Schrodinger equation again, but this time it is a slightly different Schrodinger equation. It's called time independent. You can see there is no time variable in this equation. So basically what it says is, when you apply a Hamiltonian on a state, it will reach its ground state with ground state energy. Okay, this problem may look familiar, right? So when a Hamiltonian is in a matrix and when it acts on one of its eigenstate, you will get eigenvalue times eigenstate. And now we know how to solve this equation, right? There are many ways. Okay, we are going to see one particular way here. So what are the steps involved? So we need to define these atoms using the Hamiltonian. And for that, there is a nice Python package already available. It works nicely with QuizKit. It's called Python-based simulations of chemistry framework, or PySCF. And if you want to know more about that, certainly you can visit this web page. And there are many ways of representing the structure of this molecule. One is called electronic structure, vibrational structure. There are some more couple of structures available uh, in IBM QuizKit package. We need to install a package called Nature in order to use those functions given here. So in electronic structure, basically we give much weightage to electron, and we'll treat the nucleus as a lumped mass. Okay, I mean something similar to what we do in continuous system simulation. Okay, it's not lumped mass. As a lumped parameter we are doing. But if you are modeling with full details of both proton and neutron, you will use vibrational structure. Then next step is, okay, the structure has been defined, but ultimately it has to be represented by qubits, right? So we have to map it. There are different mappers available already. Jordan, Wigner, parity, and there are different examples in QuizKit. So you can understand. I really do not know like which is good for what kind of simulation. Possibly if I do more work, I may come out with some answer and another video possibly on it. You may also ask that question, like what we do in continuous system, model order reduction, right? So in this case, the number of qubits can be reduced because we have now shortage of qubits, uh, right? So that is also possible. So now here we have defined the Hamiltonian. Next step is we have to do the Ketzai. All right. For that, again, there are transformer functions available. So, like a typical optimization problem. So, this is called ANSOS. I don't know why they call, but it's a very common term. We can also use that. And there is another function which is called, basically it combines H and Kets, psi. It's called unitary coupled cluster singles and doubles. Again, there are different ways of doing this, right? And how do we choose? Based on, of course, the physics behind it or the chemistry behind it. Since I'm not an expert in this field, I just took a, an example from IBM QuizKit and brought out here. Okay. So now we have defined both Hamiltonian and the state psi. Next, what we have to do? We need to get the ground energy, ground state energy. You may not get in one instance, so you may have to do repeatedly, and that is what is being done with the help of VQE. So VQE stands for Variational Quantum Eigensolver. Okay, it's a quantum algorithm which has got some sub functions. The first one is the estimator. So once you build this and execute in a quantum computer hardware or a simulator, you need to make measurements, and you'll be using functions, estimator function, either from primitive library or runtime library, depending on where you are doing the simulation. The molecular simulation running on a device, hardware device, you will call this one. And if you're running it in a simulator, you'll be calling from here. So from that, you find out you calculate and find out the ground state energy and check whether that is the lowest number or not. If not, you try to optimize it by choosing the different set of parameters which define the state psi, because state psi is actually parametric state wherein you can change the parameters, and those parameters are computed from these optimization algorithms. Again, there are many algorithms, not only three I listed here, there are many more, and they are all available in Qiskit library. Okay, today we are going to see SLSQP. I think in one of my previous videos, I had used Kobila. So one good thing is you just call VQE once, it will run iteratively inside that, and it will give out the ground state energy in Hartree, bond lengths, angles, and depending on whatever we simulate. There are many more things we can do apart from finding out the ground state energy. Okay. So, though initially it looked tough, like it's something why physics, chemistry coming into picture, but ultimately it's like any other computer scientist or a software engineer's problem, right? You define a matrix, you define some state, make the measurement, do some calculation classically, get some new parameters again in the using classical methods, then go back to the quantum computer or simulator, try to run with a new set of parameters, and the iteration continues till you get the answer. So putting the same thing in a different way, so we define H and the state pi, which is again state psi, which is a parametrically model. We call it as theta. So typically it is something like a rotational gate where the angle can be changed. Okay, so that is what. No, it's not. It may not be one single gate. There may be many sets of gates with different values of theta. Okay. So after defining H and the state, we make the measurement after executing all the gates, and you end up some values from which you can calculate the energy, check whether it's minimum or not. If not, arrive at the new set of theta values in a classical computer and pass on to the quantum computer. And then you keep repeating this process till you get an answer. Okay, the iterations occur, in a nutshell, what we do, the iterations occur within the VQ algorithm itself. So why I made the statement is you have to call only once, you don't have to do the iteration. The iterative steps are built into the VQ algorithm, so that makes life easy for us, right? The VQ algorithm involves preparing a quantum state, measuring its energy on a quantum computer, using a classical optimization techniques, update the parameters, and then you continue the iteration. The process is repeated iteratively until a convergence criteria is met or a maximum number of iterations is reached. We can define how many iterations we want to do. Okay, so it's very simple. The problem initially it looked very difficult, but now you can see it's very simple, and you will still like it when we go and run it on a simulator. So let me run it. So I'm going to run it in the cloud platform because I had that of time in installing the PySCF package, and I believe it's difficult or not possible in a native window environment, though it works comfortably in a Mac or in Ubuntu platform. Okay. So since I was unable to install, I started, using this code. This code was given by IBM QuizKit, so I'm going to run it in cloud platform. So as we have seen earlier, first step is we need to define the molecule. So in this case, we are going to define the hydrogen molecule. Of course, there are many examples available in QuizKit with lithium hydride or water molecule and things like that. So here we are seeing, we know that a hydrogen molecule has got two hydrogen atoms. That is what we are saying, 2H, and we need to define the space between them or the distance between them. We also need to do something more. We call it as basis STO3G. I believe this method is applicable for a lower level of elements in the periodic table, and this supports the entire, I think entire all the elements in the periodic table can be simulated using IBM QuizKit nature using PySCF, but this will keep changing. I understand from the documentation, from hydrogen to xenon we can use this. Afterwards you may have to use something different, which again will be given in the documentation. Then you can also define other parameters, because the chemists may not be just interested to know the ground state energy. They would like to know how the reaction takes place. At that time they may define different values. Okay. In addition to Armstrong, it looks like you can define other units also. So now we define the uh, atomic or molecular structure. We need to convert into qubits, right? So that is what is done by the mapper. Again, there are different mappers available. One such mapper is called Jordan-Wigner. Afterwards, maybe I can run it. It runs very fast, surprisingly. You can see here. Afterwards, we need to define the answers. In fact, by calling this UCCSD, you not only define the trial state or the approximate state or the initial state, it combines both the Hamiltonian and the states. So we also need to uh, call it in this particular format, but you don't have to really break your head, because you can see here there are no numbers associated with these parameters. We just call them, and we also call the Hamiltonian here. After it, afterwards, you just call VQE once. That's it. And of course, we are putting some initial values to it. And then VQ, we pass on the estimator from where it has to come from primitive for simulator or runtime for the actual hardware device. Answers we have to pass, and which method we want, optimization method we want to make use of it. So you pass on all this what parameters or functions, okay, or the names, you will be able to do that. Afterwards, what you have to say is just solve. All right. I'm just, oh, sorry, something happened, but anyway, it's running at, you can see here it's very fast, right? We're able to model a hydrogen molecule, and we got the electronic ground state energy in heart rate. Not only that, we got nuclear repulsion energy, total ground state energy, and some more parameters called the dipole moment and things like that. Okay, one question comes, how accurate it is, how good is this number? So again, IBM QuizKit nature, you also have some NumPy minimum eigensolver. So we are just calling for this problem. and then trying to compare the answers what you are getting from both the methods, you'll be surprised. No? They're almost equal. Even they are equal up to 7 or 8 decimals. Not only that, even other parameters also very close. So it's very nice, very simple problem. So we are able to do, like this you can do different molecules, okay? Just out of curiosity, I just wanted to run how the circuit will look like. So I just put this decompose, and of course some more level of decomposition can be done, but just to get a feel of it, the circuit has got 4 qubits. In fact, there is another example wherein they used only 2 qubits. All right, and you also would have seen any Hamiltonian can be represented with just as our set of poly matrices or poly gates. So that is what this is being seen here. Okay. All right, so we'll get back to our presentation. So as you have seen it, it's a very simple problem to do molecular modeling or molecular simulation. And these are the references I have used. Um, PySCF, very, very important one, because it works not only with Quizkit, it works with many other tools. I think not only Quizkit offers this capability of molecular simulation. I have seen it in Google Circ and PennyLens package also. I'm not sure about Microsoft and Amazon's bracket. It might be possible. Okay. And if you want to know more about, visit this page for want to know more about VQE, and the entire set will give a very good understanding of the different solvers available, mappers available. Okay. So certainly, if you want to learn more about those physical chemistry, you can do that, and very nicely documented. And if I get an opportunity to work more on this field, that certainly I'll come out with some more videos highlighting the different functions available, how to use, when to use, which one. Okay. Yeah, I think that's the end. Thanks really for watching it. See you soon. Till then, bye bye.